So we're going to continue with thermochemistry here and looking at why some reactions are spontaneous. And it's based on two big ideas. One, on the change of enthalpy of the heat of formation for the reaction. And I'll go back a couple of slides here just to remind you that the more negative the value is, like in this reaction here, the formation of water, the more negative the value is on that energy that's released, the more stable the products are, which means that I have an exothermic reaction, and nature favors more exothermic reactions, right? More negative values for that delta H. So going back here, that's what it's talking about on the first bullet, the amount of energy that's released by the chemical reaction. And again, we favor more of a negative value in spontaneous reactions. And then the second one is the randomness of particles in a system, right? And we'll talk about what that means when we talk about randomness here in the next couple of slides. And I just mentioned this here, the majority of chemical reactions are exothermic, so they have a negative value for that heat of formation, that delta H. And in these exothermic reactions, the products are going to have less energy than the reactants will. So when we talk about here in the second bullet here, we talked about randomness of particles. That randomness is referred to as entropy, and that has a symbol of S for it. So this entropy is a measure of how particles are going to become more random in, for example, in a state of matter. So like if you have a solid that has a very crystal-like arrangement, and it is transitioning to a liquid, well then that crystal-like structure is going to be becoming more random. So as a liquid, those particles are going to be allowed to move around in random different directions. And then it would become even more random if you took that liquid and you allowed it to transition it to become a gas. So there would be even more randomness with the particles movement, their motion. And so here in nature, things they're always trying to become more random. There's always more disorder in nature. You have a cup on top of your table, the cup really wants to fall off the top and break apart. It doesn't want to be a solid, uh, it wants to become more disordered, more disorganized, right? So the delta S, if the delta S is positive, there's an increase in entropy. And if the delta S is negative, there's a decrease in entropy. So you see here that my entropy wants to become a more positive value, which goes in the opposite direction of what we were talking about with the enthalpy, excuse me. So the enthalpy wants to become more negative, the entropy wants to become more positive. So those two forces are kind of always in flux with each other. If the delta S is negative, again, there's a decrease in entropy. I think I mentioned that, but I'm going to mention it again. So let's take a look at this. So if I have a solid, right? Let's just say, going back, just looking at this, if there's less entropy, a decrease in entropy, it's negative. So here we could, just say that the value for the solid is going to be more of a negative value. And as that transitions into a liquid, that delta S is going to start to become more positive. And then if I transition to a gas, that delta S becomes an even bigger positive value, right? So there's going to be more disorder as I move from solid to liquid, and more disorder, right, as I move from liquid to gas, okay? So let's see how that applies to, a couple of reactions here, a couple of equations. So if I look here at the first equation, I have 3 moles or 3 molecules of hydrogen gas plus a molecule of nitrogen gas. And these two have combined. They've combined together to produce 2 moles of NH3. So the disorder there, right? The disorder became less. So here this value would be less than 0, right? Because it's going to probably be more of a negative value since negative values, sorry about that, I keep pushing the wrong button. Oh my God. Since the negative values for, oh, went a little too far. Since the negative values for the delta S, right, for that entropy, negative means that the randomness decreased. So here in this first reaction, the randomness decreased in the going from the reactants to the products. In the second reaction, I have KNO3 is decomposing. It's breaking up into two different ions there, potassium ion and a nitrate ion. And there, so since there's going to be more randomness occurring, then that delta S is going to be greater than 0. Right? So if we look at back here at this slide, the entropy is going to be increasing, so that means it's going to have a positive value. So it's going to be greater, it's going to be bigger than 0. And then here I have again um, 2 atoms of magnesium and a molecule of oxygen are combining to produce magnesium oxide. So there the randomness is again is decreasing. So again that is going to be a value of less than 0 because it could be more negative. So that's what we're talking about here with entropy, is just measuring the amount of randomness in a system, right? So spontaneous reactions are always going to favor a more positive value, right, for the entropy, and a more negative value for the enthalpy. So if you have a higher positive here, and your exothermic, excuse me, and your heat of formation value is less than 0, then that's going to favor a spontaneous reaction. So I'm going to go ahead and skip the next few slides, and we're going to get into what's required for a reaction to occur. So if I want the reactants to produce products, right, there's certain criteria that needs to be met. One of those is that when the molecules or the atoms are colliding together, they have to have enough energy to overcome the forces that are repelling them. So they get enough energy together, they collide in the right way, then they'll react with each other. The other one is their orientation, right? They have to be orientated correctly. So for example, I'm just going to use just 2 simple lines here. These 2 lines are going to have more of a chance of reacting here, right, versus the one on the bottom. They're maybe slightly off from one another, right? That's just kind of a general view or general idea on that. So they have to have, in other words, if reactants are going to produce products, they have to have enough energy, they have to have enough, and they have to have the right orientation for them um, to react. And there's a few other factors that can influence the rate of reaction. So once the products have enough energy, that's going to be the reactants have enough energy and they oriented the right way, what are some other factors that it can influence how fast they're going to react with one another to produce products? And one of them is going to be the nature of the reactant. So for example, sodium is an element from group 1. It is extremely reactive with water, right? If I just go one more group over and I look at magnesium, magnesium's in group 2, and elements in group 2 are reactive with water, but not as reactive as elements from group 1. So magnesium's going to be less reactive than sodium. So by the nature of the reactants, it's talking about what are the reactants made of and how reactive are those elements, right there, those chemical properties that they have. Number 2 is surface area. So if I'm going to burn a piece of carbon, the carbon's gonna burn faster if I've ground it up into a powder versus if it's in a solid cube. Okay, so increasing the surface area of the reactant is going to increase the rate of the reaction. It'll allow them to react faster. In general temperature, an increase in temperature, a higher temperature is going to equal a faster reaction, right? In general, that's not always the case, but most of the time that's what we see happening with temperature. Concentration. So for example, if there's oxygen in the air, right? But it's not as concentrated as if I took a tank of oxygen and I put just strictly oxygen in there, right? That concentration of oxygen in the tank is going to be much more reactive, right? Than if I have oxygen that's spread out in a less concentration. So the oxygen tank could be 100% oxygen in there versus the air that only has about 20%, right? And then the presence of a catalyst. If I add a catalyst into a reaction, it's going to speed the reaction up. It's going to cause there to be less energy needed for the reaction to occur. So what that catalyst affects is the amount of energy that's required for the reactants to collide, right? So I'm reducing that amount of energy down by adding a catalyst. And those are going to be that's going to be it for this particular part of the thermochemical equations, excuse me, of the thermochemistry. So if you have any questions, please don't hesitate to ask, um, and I can set up some kind of a meeting with you to help you with that.